Okay, good morning. Here's the side sheet. Okay, so a lot of things for today. You have homework due today. I'm not going to ask you to submit the homework because I want you to keep it for the purpose of studying for the exam. So I didn't announce it because I wanted you to work on the problems. You're going to discuss those problems today, but you're going to keep it. You're going to grade your homework on your own to find out what type of problems you're having. Okay? So you keep your homework. I'm going to discuss the homework, but before we get to the homework, there's some material that we need to cover. This is also going to be part of the exam. Remember, the first exam is going to be on Monday at 11 o'clock, and this is the last material that is going to be included in the exam. So, on Monday, we started discussing discrete probability distributions, and we get to the point in which we were describing basically defining what is the probability mass function and what is the difference between the probability distribution and the cumulative probability distribution. So I'm going to start from there today. And again, there are some problems in which we are interested in finding the probability of the observed value of a random variable that will be less than or equal to some real number. So instead of looking at the equality at that exact number, we are interested in finding the probability of that random variable being less than or equal to some real number, x. And that's what we call a cumulative probability. So writing that probability, we're going to use a capital F. This is a function of x, and that basically means that the probability of that random variable will be less than or equal to that exact number. For every real number, and we define that as the cumulative distribution. So, talk about these examples. We define the values for the random variable for each specific problem. We computed the cumulative probability find, for instance, the cumulative for 2, which is find the probability that the number of correct matches is less than or equal to 2. So for the discrete probability distributions, we were adding the probability of having 0 and the probability of having 1, which in that case is 5 over 6. And if you were to also look at the cumulative of events being less than or equal to 3, then you're going to add 2 over 6, 3 over 6, and 1 over 6, which are the probability of all the events, and that should be equal to 1. Because you are considering all the outcomes of your sample space. The thing that I believe is going to be more difficult for you to understand is how to define the cumulative distribution for a specific problem. And the idea here is to express the cumulative probabilities, in this case 0, 2 over 6, 5 over 6, and 1, for each outcome. So in this case we have 0, 1, 0, 1, and 3. Those are our outcomes. So we want to define the cumulative probability for each outcome. So we know that an outcome being less than 0 will never happen. So that has a probability of 0. Then an outcome that is including 0, but less than 1, will happen only with a cumulative probability distribution of 2 over 6. An outcome that is within 1 and 3 will happen with a probability of 5 over 6, and greater or equal, or m greater or equal to 3, has a cumulative probability distribution of 3. Okay? So today we're going to have another example. We work on the same type of problem. This is a different case. And we basically perform the same steps. We found the cumulative probability distribution for each outcome. And then we express the cumulative probability distribution based on the probability of each outcome. So I think it's very helpful in order to understand the difference between these two concepts to look at the graph. So if we define, excuse me, if you define the probability distribution based on the outcome, so these are your x, without looking at the cumulative probability, you know that based on this graph, this is coming from our previous example, this one. If you look at the probability of having x equal to 0, that will be 1 over 16. If x is equal to 1, then that will be 4/16. X equals 2, 6 over 16, and so on. So these are the probabilities for when the random variable equals a specific number. Now, if we look at the cumulative probability distribution, that is going to look at like a step or a ladder for the graph. So now we're going to start adding the probabilities for each outcome. So again, for 0, you're going to start with 1 over 16, which will be this line. And that will include 0 and all the numbers until you get to 1. So once you reach 1, then you're going to add the probability of 0 plus the probability of being equal to 1. And that probability equals 1/16 plus 4/16. So that will be 5/16, which is this point right here. And you'll still there until you reach x equals 2. At that point, you will go up because you're going to add the probability of being equal to 2, and so on. Until you reach the probability of being equal to 1, which is your complete sample space. Okay, so these are the ideas. Again, the probability distribution, you look at the probability of x being equal to a number that gives you the probability for each outcome, so 0, 1, 2, 3, and 4. But when you look at the cumulative probability, then you're looking at, for instance, for 2, you're looking at the probability of 0 plus the probability of 1 plus the probability of 2. You are accumulating those probabilities. Same thing for 4. So when you look at the cumulative probability of 4, you are adding the probability of 0, 1, 2, 3, and 4. So you are accumulating those probabilities. Okay? So let's discuss another problem or example. Okay, so in this case we have the sample space of a random experiment. So the sample space is defined by these letters A, B, C, D, E, and F. And the problem is telling you that each outcome is equally likely, which means that we'll have the same probability. And a random variable is defined as follows. So if your outcome equals A, so let's say you have these letters in a box, and you pick A, select an A, then if you give a value to that A, that will be 0. And this is defined by the person performing the experiment. So selecting an A, that will give you a value of 0. Selecting a B will give you a value of 0. C 1.5, D 1.5, E 2, and F 3. So those are the values for the random variable. Okay? So the problem is asking you to compute some probabilities. So determine the probability mass function of X. Use the probability mass function to determine the following probabilities. So as I explained on Monday, when we refer to a probability mass function, you need to know that we are dealing with a discrete probability distribution. Because the term mass function or probability mass function is always denoting a discrete probability distribution. Okay, and you're going to see the difference in a few minutes when we talk about the continuous probabilities. So the problem is asking for the probability of x being equal to 1.5. So if you know that these outcomes are all equally likely, meaning that they have the same probability, can you tell me what would be the probability of having x being equal to 1.5? 2/6 or 1/3, correct. So that would be equal to the f of x being equal to 0. Actually, it's not the right notation. So f of x, when x equals 0, that is the probability of x being equal to 0, and that happens because you know that each outcome will have the same probability. So this is 1/6, 1/6, 1/6, 1/6, and 1/6. So for those outcomes, you know that 0 happens 2 times. So it's going to be 1/6 plus 1/6, and that will be equal to 1/3. Yes, sir.
Why is that related to 1.5?
Oh, I'm sorry. I was looking at, yeah. Shouldn't be. Yeah, this should be 1.5. Sorry. Good. Yeah, I'm confused because you have the same probability. Yes, but the problem is asking for the probability of x being equal to 1.5. So in that case, you're going to look at the outcomes. So you have 2 outcomes out of 6 that has x equals 1.5. So you add those 2 probabilities. So it's 1/6 plus 1/6. That will be equal to 1/3. Thank you. Any questions? Okay. So let's look at the next one. B says what is the probability of x being within 0.5 and 2.7. Any ideas? So you have, again, these outcomes. And you have to look at how many of those outcomes are within this range. So it will be this one, and this one. So that equals 1/2, correct? So let me put that here. So this is a probability of 5x 2.7. So you have 1.5 and f of 2, which is 1/3 plus 1/6, and that is 1/2. Because the only outcomes that are within that range are 1.5 and 2. So you're going to add the probabilities for all the outcomes that are within that range. So we have C, D, and E. So we have 3 outcomes that are within that range. You add the probability of those 3 outcomes, and that will give you 1/2. In part C, probability of x being greater than 3. Zero. Where is the assignment sheet? Yeah, I'm gonna pass another one. I don't like when students try to take advantage. So if you leave the room and you're planning to leave the room, please don't sign in. If you came late, please keep your homework because we are going to discuss it and I'm not going to collect it. I want you to keep it for you to study for the exam. Okay? So we're going to go over that by the end of the lecture today. So problem, so part C again, probability of x being greater than 3. That's an outcome that is not part of our sample space. So that means that there's no probability that that event will happen. So the probability is going to be equal to 0. Is that clear? Does that make sense? Okay. Part B, x so this is similar to part B. So what you do is you look at the outcomes one more time and you check which one satisfies this range. So 0 is included. So it will be this one, and these two. 1.5 is less than 2 and greater or equal to 0. So it will be these 4 outcomes. Because 2 is not included. So in that case we have f of 0 plus f of 1.5, and that is 1/3 plus 1/3, 2/3. Then part E, the probability of x equals 0 or x equal 2. So in that case, you need to add the probability of x equals 0 and the probability of x equals 2. So x equals 0 is 2/6 or 1/3, and x equals 2 is 1/6. So that would be f of 0 plus f of 2. And that is 1/3 plus 1/6. Okay, any questions? Now I want you to try this on your own. Try to define the cumulative distribution function. And if you have a piece of paper, please work on it on a separate piece of paper. And if you get it right, I'll give you a bonus point for our exam on Monday. So I want you to define the cumulative probability distribution, or try to define it. What I'm looking for is something like this. So you want to define the cumulative probability and those range. Okay, so give it a try. I know it's kind of a challenge, so try it. I'll give you 2-3 minutes. And again, if you get it right, I'll give you a point. In the meantime, I will pass the homework. So I have homework 2 here. Jaime, Anthony. Doug here. James. Corona. I posted the homework solutions. If you have questions, let me know. Mark, Ryan, Philip, Edward. Richard, Leonardo, Kyle, Merritt, Juan, Shelby, Lori, and Tom, Trevor, Louis, Beth, David, Denise, Seth, Seth, Andrew, Javier, Mayor, Tiffany, Ryan, Joel, Ryan, Ryan, Andrew. Okay. Yeah. If you gave me your homework 1, I already made the changes, so I have the homework here. You can talk to me at the end of the lecture. Okay, so you can pass that sheet of paper if you have it. If you want to submit it, you still need more time. Okay, I'll give you 1 more minute. Okay, hands up. And don't forget to put your name. Anyone else? Okay, so anyone else? Okay, so I'll take a look, and again, if you're able to get it, I'll give you that point for Monday. Okay, so what we're trying to do here is the following. We have some community probabilities, and we also have some outcomes. So we know our outcomes. We know that the outcomes are 0, 1.5, 2, and 3. So those outcomes are going to define the range of our probabilities. So we are looking at f of x question? Well, yeah, we're working on this problem. No, I was asking for this cumulative distribution. Sorry, yeah. So, okay, so let's try to understand this, right, really quick. So we need to define the probabilities on this side. So here are the probabilities. These probabilities are cumulative. And we need to define the range for outcomes. So we know our outcomes. We always start with an outcome being less than 0. Then we have an outcome in which 0 is included, and the next outcome we have is 1.5. Then we have 1.5 is not included, actually included, x. Our next outcome is 2. Then we have 2 included. Our next outcome is 3. And then 3 greater or equal to 3. X greater or equal to 3. So these are coming from those values for x. Now I want to know the probabilities of being within these ranges. And these are cumulative probabilities. So the probability of x being less than 0, 0. We don't have any outcomes that are less than 0. The probability of being within, including 0 and 1.5, that will be 1/3. Then the probability of, or the cumulative probability for 1.5, I think we computed that somewhere here. No, it's not here. So that will be 2/3. The cumulative probability for 2, including 2 and not including 3, is 5/6. And then greater or equal to 3 is 1. So the way you get these probabilities, again, 0 included, so that will be f of 0. We know that equals 1/3. F of 1.5 equals 1/3. F of 2 equals 1/6. And f of 3 equals 1/6. So the cumulative for 1.5 will be equal to f of 0 plus f of 1.5. And that is equal to f of 0 is 1/3 plus f of 1.5 is 1/3. So that is 2/3. So for the cumulative where f 1.5 is included, which is this case, the cumulative is 2/3. Yes, sir.
Isn't the one plus the next less than?
This one? No, it has to be greater or equal. Because
It's greater than
this one or this one? The bottom one? You need to include 3, and you know after 3, the probability will never go higher than 1 because that's the maximum. You will never have a probability greater than 1. So once you reach 1, any value, yeah, it will be 1. So what we're trying to do, if you look at the graph, remember, let me try to put it here so you have copy. So new slide. So we're going from the and I noticed that some of you already did this. So remember what we're trying to go is from this histogram. This one does not represent the problem. This is just to give you an idea to this graph. Right? So when you look at this problem, you know that for 0, say 0 is here, this is actually 0 should be here. Then here you will have 1.5. Then you're going to have 2. And then you're going to have 3. So once you reach this point, you know this probability is 1. So once you get to 3, that probability is 1. Any number that happens after 3 will already reach the top. So there will be no higher probability than 1. So for our case, for 2, this is 5/6. For 1.5, this is 2/3. And for 0 is 1/3. So for 0, you know the probability is 1/3. For 1.5, the probability is 2/3. And for 2, the probability is 2. And for 3, the probability is 1. And this is what we're trying to do when we write the cumulative function. We're trying to express this. So if you tell me my outcome is 1, what is the probability of having 1 based on this graph, or the cumulative probability of 1 based on this graph? You know it will be between these two, so 1/3. Remember, these are cumulative probabilities, okay? So that will be the probability of being less than or equal to 1. Here, the probability of being less than or equal to 2.5, you will come here. Less than or equal to 2.5 is 5/6. Less than or equal to 1.7, come here, 2/3. Okay, so that's the use of the function and also the graph. Okay, so again, I'm gonna post these notes today, all the notes for the lectures that we already discussed in class for the exam. this is going to be part of those lectures, and I'm going to post the video for today's lecture as well. So if you need to go back and review it, you will be able to do that. Okay, so any questions so far? So we are looking at discrete probability distributions. Just another problem, really quick here. So we have a probability mass function. This is a discrete probability distribution, and we have 4 outcomes, 5 outcomes, 0, 1, 2, 3, and 4. And again, I'm asking for some probabilities based on that function. So the first probability is the probability of x being equal to 4. So if you have a function defined in that probability, what would you do? It's just going to be f of 2. 2x2 plus 1 divided by 25. So that probability is 9 over 25. I'm sorry, yes. Thank you. Probability of x being less than or equal to 1. Then for that one you need f of 0 plus f of 1. Because these are your outcomes, 0, 1, 2, 3, and 4. So you need to consider the cumulative up to 1 when 1 is included. So that will include 0 and 1. So for that case is 2 times 0 plus 1 divided by 25 plus 2 times 1 plus 1 divided by 25. So this is 1 over 25 plus 3 over 25. 425. For C, probability of x being within 2 and 4 when 2 is included and 4 is not included. Okay, so you need to pay attention to that signs. So that would include 0 plus, I'm sorry, this is 2. Two plus f of 3. 4 is not included. So that is 5 over 25 plus 7 over 25. That's 1225. And part D, probability of x being greater than negative 10. So again, this is a cumulative probability. So in this case, if you look at the graph, this is a negative number. So let's put negative 10 here. And let's say that our probability is starting 0, 1, 2, 3, and 4. Let's say you had this graph. Where this is 1. So if you're looking at the probability of being greater than negative 10, you will include all the probabilities to that side. So which means that you're including all the outcomes. So if you include all the outcomes, what will be that probability? It's 1. Correct. Any questions? Okay. I think we have one more example. The assembly consists of 2 mechanical components. Suppose that the probability that the first and second component meet specifications are 0.95 and 0.98, assume that the components are independent, determine the probability mass function of the number of components in the assembly that meet specifications. So the question is, determine the probability mass function. So I'm not asking for a cumulative probability, I'm asking for the probability of being equal to something, of the number of components in the assembly that meet specifications. Okay, so we have two components. So our outcomes for this sample space are very limited. We can have, let's define x equals the number of components that meet specifications. So if none of the components meet specification, we can compute a probability. If one component meets specification, we can compute the probability. And if two components meet specification, we can compute the probability. Okay, and we have these numbers. One for the first component and one for the second component. So the first component meets specification with a probability of 0.95. Second component meets specifications with a probability of 0.98. So the probability of none of the components meeting specifications will be equal to, these are independent components, so we can use the multiplication rule to find that probability. So that will be, let's define first meet specification equals 0.95, and I'm going to call this A. Probability of second meet spec equals 0.98. That is called B. So the probability of none of them meeting specification will be equal to the probability of A complement times the probability of B complement. Remember the complement? What that means is that if the probability of meeting specification is 0.95, the complement of that probability is 0.05, and for the second case is, this is 0.98, 0.02. So this is 0.001. Probability of x being equal to 1, then we can have one of the two being meeting specification and the other one not meeting the specifications. So for the first one, let's say the first one does not meet specification, but the second one does. And we also have the case in which the first ones will meet specification and the other one will not meet the specifications. So that probability is 0.068. And the probability of both of them meeting the specifications will be just 0.95 times 0.98, which is 0.931. So the probability mass function is just x f of x 0, 1, 2, and that will be 0.001, 0.068, and 0.931. Seeing a lot of scare faces from this area. I know we're running out of time, so what I'm planning to do is to have a review session on Friday. So I'll give you an opportunity for you to go review, and you can plan to meet
maybe in this room in the afternoon on Friday, and we can go over the problems of the homework, and you're gonna have the chance to ask questions. Okay, so I'll send an email. Friday afternoon works for all of you? Okay. So I'll send an email, and yes, sir.
The solution.
Will be posted, yes. Okay, so that's the last example for these, for the discrete case. Now we need to go over the last material, which is continuous probability distribution. So we already discussed the discrete case, discrete probability distributions, but we know that there are some random variables that are continuous. Okay? So for those cases, we also have a different type of distribution. So continuous random variable has a probability of 0 of assuming exactly any of its values. Okay, so in the example that we discussed before this slide, you are computing the probability of x being equal to 0, and you can compute the probability for that number, because that is a discrete random variable. But when you have a continuous random variable, you will never be able to compute a probability of a number, of a random variable being equal to a number. And I'm going to try to give you an idea of why that's the case with this example. Okay, so consistently, its probability distribution cannot be given in a tabular form, just like we did for that example. Okay, so let's discuss a random variable whose values are the heights of all the people over 21 years of age. Okay, so between any two values, say 163.5 and 164.5 centimeters, there are an infinite number of heights, one of which is 164 centimeters. So you can have an infinite number or an infinite amount of numbers between that range. Okay, this is a continuous random variable. Remember, we are measuring, so we can have any numbers between those two that are our limits. So the probability of selecting a person at random who is exactly 164 centimeters tall and not one of the others is infinite large. Or that should be infinite small. It will be really, really small. The set of height so close to 164 centimeters that you cannot humanly measure the difference is remote, and thus we assign a probability of 0 to the event. Okay, so you're considering a continuous random variable. There's no way that you can define an exact integer number for this random variable. The probability of selecting a person that is an integer value will be really very small. So for that cases, we assume that that has a probability of 0. Okay? So for the continuous probability distribution, we concern ourselves with computing probabilities for variance intervals or continuous random variables. So instead of looking at the equality, you're going to be looking at the range. So we're going to use probability of this range, a and b at the limits, or greater or equal to another limit, and so forth. Something that is not the case for discrete random variables, but is the case for the continuous random variables, is that when you compute the probability and you're including the limit, it will be the same as not including the limits. So it will make no difference. It will have the same probability. Okay, so having the limit, the inclusion sign, is the same as not having the inclusion sign for the probability of a continuous random variable. Okay, that's not the case for discrete, it's just for continuous. So the probability distribution of a continuous random variable cannot be presented in a tabular form, but it can be stated as a formula. Okay, so the formula is a function of the numerical values of the continuous random variable x. So f of x is usually called the probability density function or simple density function of the random variable. So remember, for discrete random variables, we were using the term probability mass function. Okay, so that term does not exist for continuous random variables. For continuous random variables, we use the term probability density function. So if I ask you about a probability density function, you should know that we are talking about a continuous random variable. Okay, so that term right there is very important, probability density function. So most density functions that have practical application in the analysis of statistical data are continuous. And for those density functions, instead of seeing a histogram or a bar chart, you're going to be seeing continuous functions like this one. So it will be some curve or any shape. The probability density function is constructed so that the area of the curve bounded by the x-axis, just like here, the area under the curve is equal to 1 when computed over the range of x for which f of x is defined. So what we are saying is that the area of the curve will be equal to 1, and the area under the curve is going to give you the probability of a continuous random variable. Okay? Any concept or strategy that you have learned from calculus that will give you the area under the curve? Integration. Okay, so for continuous random variables, you're going to be integrating to find the probability. So the shaded area on the density function between the ordinate x equals a, x equals b from an integral calculus is given by the integration for those limits a and b of the density function with respect to x. Okay, so this is a definition for the integration. Okay, so instead of adding f of 1 plus f of 2 plus f of 3, and this is the probability, now we're going to be integrating on the curve to get the probability of a continuous random variable. So this is the formal definition. So function f of x is the probability density function, or PDF, for the continuous random variable x, defined for a set of real number. If it satisfies these three conditions, f of x is greater or equal to 0. The integration for the negative infinite to infinite is always equal to 1. So the probability will never be greater than 1. And the probability within those ranges is defined by the integration. So let's look at this example. Suppose that the error in a reaction temperature in Celsius for a control lab experiment is a continuous random variable x having the probability density function defined as x squared divided by 3 for -1 to 2 and 0 elsewhere. So the first thing that I want to do for this problem is to verify that f of x is a density function. So the only way that I have to verify that is by looking at the definition. So I need to find out if f of x is greater or equal to 0 for all the x, and if the integration of that gives me 1. So let me show you that. So I'm going to verify if there is a continuous or a density function. So A, first item, f of x is greater or equal to 0 for all x. So what I'm going to do is just integrate, well, not integrate, but find the probability of -1 and find the probability at 2, which are the limits. And if if that function is greater than 0, then the first condition is satisfied. So f of -1 equals -1 over 3 squared. So that is 1/3 and is greater than 0. And f of 2 equals 4 over 3, and this is greater or equal to 0. So the first condition is satisfied. The second condition
is that the integration from minus infinite to infinite of f of x dx equals 1. So for this problem, the limits of the function are defined for minus 1 to 2. So you use those limits. F of x is x squared over 3 dx. If you integrate that function, that will give you 1. Okay? Do you want me to show you how to integrate that? So that will be x squared, x cubed divided by and you need to evaluate the limits. Okay? Okay, so the second part is find the probability less than x less than or equal to 1. So again, to find that probabilities, you need to integrate for those limits 0 to 1, x squared over 3 dx. So that will be x3 over 9, evaluated for 1 to 0, and that is 1 now. Okay, so for continuous random variables, we're gonna have an integration. If I ask you the probability for this function that we know that is a density function, it's a continuous random variable. If I ask you the probability of x being equal to 1, what will be your answer? X equal to 1. The probability of x being equal to 1. 0. Probability of being equal to one number, any number, for a continuous random variable and a continuous distribution is always equal to 0. If you integrate and you're asking, remember you find the density function, you find the probability using integration. If you integrate and let's say the limit is the same, what will be your answer? It's 0. Okay? So probability of x being equal to 0, or 1 or 2 for a probability density function is always 0. Okay, so now let's define a cumulative distribution. Same concept for a continuous random variable. Then what you do, again, instead of summing the probabilities for that range, you integrate up to a certain point. Okay, so if I ask you the probability of x being less than or equal to 3, then you will integrate from minus infinity to 3. That will give you the cumulative probability up to that limit. Okay. So this is another example. The Department of Energy put projects on the bid and generally estimate what the reasonable bid should be. Call the estimate B. The DOE has determined that the density function of the winning bid equals this function. So here we have B. B is a constant. Okay, so it will be equal to a number. It's not a variable. So find f of y and use it to determine the probability that the winning bid is less than the DOE preliminary estimate of B. So for that problem, what we're trying to do is to find that probability, that cumulative probability, f of y, and we're going to use that probability to determine the probability of y being less than or equal to b. And again, b is a constant, it's a number. It's just like saying 5, 3, 2, but we are using a letter instead of an amount. Okay, so f of y, or the cumulative, for this distribution is defined by 2
5, that's my lower limit. Again, b is a constant, it's not a variable. So 2, 5 times b up to y. Okay, so we go back here to the definition. F of x is going to go from the lower limit up to x. And then in this case, we're using y, so we're going to go up to y. Okay. And the function is 5 over 8b dy. So if you integrate, this will be equal to 5 8b t evaluated and y to be over 5, and this is 5y over 8b minus 5 times 2b over 5 divided by 8b. So this function or cumulative function equals 5y divided by 8b minus 1/4, and this equals f of y. So that's my cumulative function right there. Okay, so we are integrating. You're looking at the cumulative function. You're going to integrate from the lower limit to y. Maybe you can get confused here because I'm using t, but what I'm trying to use to define a variable. So you can substitute your y. Okay, so don't get confused. So once you solve that integration, then you get this f of y, which is this function. Okay, so that's our cumulative. So now I want to find the probability of y being less than or equal to b. So that will be equal to f of b, which is 5b over 8b minus 1/4, and this is 3/8. Remember, b is just a constant. It's just like it was a number. It could be 5,000, 5 million. You can treat it as a number. Any questions? Okay, so we are applying the same concepts. The only difference now is that instead of summing, we are integrating. This is the continuous cumulative distribution function. So instead of looking at steps, now we have a continuous function. And again, the top will be always equal to 1. Okay. This is another example. So the diameter of a particle of contamination in micrometers is modeled with the probability density function. This is the density function. So again, once I state that it's a density function, this is a continuous random variable. So with this, if you know this already, then you can determine the probability. Okay, so I'm going to work on the first two. And on Friday, if you have questions, we can discuss the last two. But it's just the same concept. So again, this is my function. F of x is equal to 2 over x over 3. And this is for x greater than 1. So the first question is the probability of x being less than 2. So you know that this function is defined for any number greater than 1. So that's your lower limit, right? So for computing this probability, you're going to look at, this is your line segment, this is 1. So this function is defined for any number greater than 1. So if you're looking at the probability of x being less than 2, then you're looking at this area. So your limits are going to go from 1 to 2, 2 over x cubed dx, and this is 0.75. Does that make sense? Okay, so you always have to be aware of the limits of the function. In this case, x is greater than 1. That will be your lower limit. B, probability of x being greater than 5. What do you do now? How do you define your limits? What's your lower limit? 5, correct. Because you're looking at 5 and you're looking at the probability of being greater than 5. So your lower limit is 5. What's your upper limit? Infinity, correct. So if you integrate dx, that will be equal to 0.04. If you look at this function is something like this. Okay? And we are looking at 1. So we are looking at the area under this curve. And as you go farther from 0, you know that the area is going to go very small. So for x being greater than 5, you know the area is going to be very small. So that probability should be very small. Okay? So that's to give you an intuition of what's going on. Now, if you look at the first part, x less than 2, you'll be here where most of the area is. So that probability will be greater, or be 0.75, larger probability. Okay? So I'll let you work on C and D. And let me go to the last one, because this one is a very important problem. Just to give you, see if you can understand the difference between cumulative and density. So what I'm showing here is, suppose the cumulative distribution function of the random variable is given by this. That is a capital F, which means that is a cumulative probability function. It's not a density function. Okay? So if you're going to compute the probability using the cumulative function, do you need to integrate? Remember, if you have the PDF, you integrate to get the cumulative. So if you already have the cumulative, you don't have to integrate. Right? So that function is going to give you the probability. So what you do with this type of problem, since you already have the PDF, the cumulative distribution, for A, it's asking for the probability of x being less than 1.8. You just have to evaluate the function in 1.8 because that function is already integrated. That's your cumulative. Okay, so that will give you the area. So let's say this function is something like this. That is already giving you, let's say the first one is 1.8. The cumulative is already telling you for 1.8 this is the area. That's the probability. Okay, so you evaluate your cumulative at 1.8, 0.25 times 1.8 plus 0.5. And that is 0.95. Again, 1.8 is defined for this range. So you use that function. Okay, let's look at part C. What will be the probability of Z? That's correct. Why is that? Because for x less than -2, probability is 0. Again, if you have the cumulative probability distribution, you don't have to integrate. And I will let you work on the other two, because I want to spend the last 5 minutes on the outline for the exam. So this is the agenda for this lecture. We covered these concepts. Don't get scared. We haven't talked about this part yet. We're going to talk about that after the exam. Okay, so joint probability distribution is not part of this exam. Okay. So let me show you. You have these slides available already. So the exam is on Monday, and this is the outline. Basically, you're going to have two sections. The first one is a true or false, 10 questions. And the second part is 4 problems. These problems can be short answers. I can ask you, what is the probability density function? What is the difference between a density function and a mass function? Which is some stuff that we have discussed in class. If I ask you what is the difference between a probability mass function and a probability density function, you know that the mass functions are for discrete random variables, and the density functions are for continuous random variables. Okay? So that's the type of concept that I can ask you in a question. Well, I would say you choose one problem like that one, and the other two will be problems similar to the one we have discussed in class or in the homework. Okay? So the lectures basically cover this material. So these are the outlines for the 3 lectures, 5 lectures that we have covered until this point. So you can go over these topics, review the best way to review or to study for this exam, review the lecture notes. We'll make those available today. If you don't have some of the notes. Study the labs, study the homework. If you have questions, send me an email or go to my office. But you need to bring a handwritten 8.5 times 11 formula sheet. You can use both sides. You have to turn in your formula sheet with your exam, and you can use your calculator. The exam is closed to books and notes. You're allowed to use your formula sheet. And the only other item that you can have in your desk is your calculator. This is very important. You need to show your work. That's the only way that I can give you partial credit. If you have only one number, you can show me the work. I will not give you full credit because I don't know where you get the answer. And also, if you get the answer incorrect, then you will miss all the points. So, show your work. I can follow your work. I will give you some partial credit. Any questions? Yes.
2 questions. One, on the formulas, are we allowed to use words to describe it, like if x is a positive integer or like the name formula?
Yes,
like that?
you can do that. The only thing that I don't want to see are definitions of random variables, so that type of thing.
Question number 2, it says show your work. We have calculator that can integrate. Do you have a problem with us doing that?
That's a great question. So if your calculator integrates, you can use it. You don't have to show your integration, okay? But you need to show the steps of what are you doing. Like, this is my integral, the limits go from this point to this point, and this is how I take my integration. And then you can provide your answer. That works also for students that don't have a calculator that do integration. That's your case. If you're not able to complete the integration and you show me the right integration with the right limits, I can give you all the points. Okay, so that's why it's very important I'm not going to evaluate you for integration.
We're gonna evaluate you for the concept from this class. Okay? Any other questions? But remember, you need to show your work. One last thing. It's Friday. Is Friday 3:30 a good time for you? Oh,
The buses stop running at night.
at what time the buses stop running? But the thing is, in the mornings, I don't know if all the classrooms are occupied, the go classes. I'm pretty sure in the afternoon they are available.
Would you post the review session, like the video from it?
That's something else. I can go over the problems in a video and post the video, but I don't know if you want to have an interaction with me. What do you guys think? Interaction? Okay. So if you don't come to the review session, I will post the video anyways. So, but I will wait. You have to wait until Friday. So I will say Friday, 3 o'clock in this room, and then if you don't have the room available, I will send you an email to see where we can go. Okay?
So you're posting the video after your review?
After the review session. Yes. That's the homework? Sir, I'm not collecting homework 3. This is for you to keep. You can bring it on Friday because we're gonna discuss the homework, but I'm not collecting that homework. Okay, thank you.
I just have a quick question.
Sure.
About this problem in the homework. It says, let me stop the recording.